Hey, how's everyone doing? Woo! Thanks for coming to the talk. So the talk is two parts. The first part will be mostly about the physics. I'll try to avoid using jargon, using physics concept, using math. The, the key is to deliver the intuition, so you should make it feel it makes sense. And the second part, I will hand over to my friend Rick, who's an engineer, knows everything about engineering detail. So for that part, everything will not only make sense, but also practical. Unlike me, I talk stuff, but those things may not be practical. So what you see here in the background is the ion trap we use. It's kind of like the CPU you buy, like i7, i5, and you put it into the hard components, as a hard component, put it into your PC. Quantum computer, for us, is this thing trapping ions, using it as qubits. And then a lot of peripheral electronics control stuff, vacuum stuff to control. We'll cover those. We have this thing at the IonQ table. So if you're interested and you want to actually see the real quantum computer processor in 24K gold, take a look there and we'll answer any question you have. Yeah, all right. So IonQ is a publicly traded company. Making a disclaimer making me kind of lame, so I just put some cute animal there to distract you and make you still feel I'm a cool person. Yeah. In practice, all it says is if you listen to my talk, don't base on it to go buy or sell IonQ stock. That's really what it says. Yeah. Everything is on the internet, is published material. Okay, what is quantum computing? If you go and Google quantum computing, this is what you're going to get. I'm ion trapper, so I would just call it a bunch of spaghetti coated in gold. It looks fancy. It's it's superconducting quantum computer. It's good. But what I want to tell you is the world of quantum computing is way more diverse and way more than that. And today I want to help you experience that, and particularly focusing on ion trap. Yeah. But before that, let's first have I would say, the shortest possible crash course in quantum computing. What is quantum computing, right? In classical computation, every device, our cell phone, computer, whatever it runs, it uses classical bits to represent computation. Your logic, your everything is break down to 0 and 1. A bit can be 0 or 1, and you apply logic gate onto it, and that do the computation for you. With quantum computer, the qubit can be in superposition. So each qubit can simultaneously be in 0 or 1. It can be like 90% 0, 10% 1, or any arbitrary composition. And another key element of it, it's not only superposition, but it's also coherent. So your 0 and 1 have a phase difference between them. So superposition and coherent with phase. That's the two essential elements of qubits that set it different from classical bits. And we'll see very soon how you take advantage of that. So classically, if you want to solve a problem, if we treat it as a black box, the computation, you kind of give it an input of the configuration you want to try, to hopefully it's your solution, and you apply some kind of function, some computation procedure through it, and you get the answer according to that input. That's just one way of how you would solve it, kind of a universal way. Yeah, but there are many problems that it's very hard to find any structure to identify which is the actual configuration that you want, that give you the proper output, right? Say traveling salesman problem, what is the shortest path? Essentially, you have to try all the combination of the Tor and check each one of them. And then you will see which one is the shortest. With quantum computer, because each bit can be in superposition, so you can if you have one bit, you can represent two input states simultaneously. If you have 2 qubits, you can represent 4, right? 0, 0, 1, 0, 0, 1, 1, 1. And if you have 8, etc., the number of states you can represent grows exponentially. And the states, you can simultaneously use them as an input. And if you have a quantum computer, then your logical gates can handle superposition. It can process the superposition, And essentially, you treat it as a quantum black box. It processes all the input together and give you a giant superposition of all the output. That's kind of like in quantum computing, people say like a way to butcher quantum computing because it's so much oversimplified, it's so not true. But honestly, it's oversimplified, but it's true in my personal opinion. Okay, so in some sense, it's kind of like a non-deterministic Turing machine, right? Non-deterministic Turing machine, it explores all the possible computation trajectory, and also magically, it pick out the right one to give you the answer. But quantum, you just have the superposition. The property of quantum goes, if you measure it, you get any one of them. You randomly get one. So if you have a very hard problem that you want to find a hard answer, you get that answer in your superposition, but more than likely, you're not going to get that if you measure it. It's in your superposition, but you just cannot get it. Luckily, you can run quantum algorithm. Remember we talked about the phase? So in physics, anything have phase, you can create this interference, right? So it's like a wave. If you have two waves go together, they interfere, some part get amplified, some part get suppressed. The ultimate hope for this, at this point, when you have a giant superposition of all your answer, is you can design a very, very magical way to use quantum gates to induce such interference. So at the end, all the unwanted answer is suppressed. Only the answer you want is enhanced. So that's how you can possibly take advantage of this giant quote-unquote parallel computing machine. But reality is we don't know, for most of the problem, we don't know how to perform such interference. There are some algorithms we know. For example, Shor's algorithm that factor a large number kind of do so. Yeah. And then back again to what we covered, the elements is you need to have qubits that can be in superposition, both 0 and 1, and you will have to keep it coherent. So the phase information on there is intact, that you will later use it for interference to do your algorithm. And your gates have to be able to handle the superposition, have to be able to handle the phase properly, like faithfully. So we need to get the qubit, and we need to do the gates. So for quantum computing, the universal gates, people kind of like to think the quantum state as some, like, in terms of a Bloch sphere, you can think it in terms of rotation. So the universal gate set, we have single qubit rotation, which is arbitrary rotation on the Bloch sphere. And also, you can't just do computation with individual qubits or stand-alone separate qubits, right? So you have to have some gates that acting on multiple qubits to actually make your state talk with each other. So you can actually do computation, just like classical computation. And that's what and the elementary units, gates we use to do that is 2-qubit gates. C0 is one possible option. You also have many other options. So there are many, many universal gate set. But like a nice way to look at it is you just need arbitrary rotation on single qubit and anything that make 2 qubits talk to each other. So next, I will go to introduce how we do that with ions. Okay, so actually, not only ions can do that, right? Like superconducting qubits, superconducting device, we saw the spaghetti at the beginning. They use superconducting wires to represent 0 and 1 and do gates on those. You can also have many, many other technologies. At this point, some of this technology are kind of getting more advanced than others, but I think still we can think both of them as possible candidates. And each of them have different pros and cons. For example, some of them, it's easier to scaling up, means making more qubits. Some of them, it's easier to control, means it's easier for you to make your gates higher fidelity. Okay. And different modality, different technology actually looks very differently. I think they're all pretty beautiful. On the left corner, you have like a diamond MV center quantum computer. It's beautiful because it's literally a piece of diamond, and they dope it with like impurity to make it actually have different color. It could be black or pink. And here on the left, upper corner, it's what ion trap quantum computer actually looks like on the laser delivering part. And you have an ion trap, and you have photon computer. That one version of it made of like many, many mirrors. And you have superconducting, and you have neutral atom quantum computers. Look very different, right? It's kind of a very nice, diverse, exciting field. Then here comes another joke. Well, if the industrial designer you hired all hang out at the same bar, then here you get, well, it all looks the same. Well, okay, but then because I work for IonQ, so I'm going to focusing on IonQ. Let's try to open up the IonQ box and see what it looks inside. Okay, so if you remember the title page, I said it's an ion trap, right? Ion trap, we trap ion with it. The ions floating on it is the qubit we use to do computation. And here is a camera image, a video footage of actually a chain of ion trapped in there. Okay, there's a 32. I didn't count, so I'm going to skip this slide so you don't count either. Okay, so here is a 3D rendering video of what computation actually means for us. It's quite different from the normal concept of computation, right? Basically, this is a trap. We float the ion in there in vacuum, so no other particles ram into them. And your computation is literally performed by laser carrying control passes into the qubit. You saw the qubit, you saw the beam going through them. Each beam is delivering a microwave train of control information onto your qubits. And that's how you do the gates. And let's take a deeper look at another cartoon or animation. So, okay. Play, Jesus. Okay, here we go. So when you do computation, you first trap your ion, and you initialize them with some kind of laser, and then you literally just shine laser on each of the ion. If you want to run a single qubit gates, you shine a single laser on that single ion. If you want to run two qubit gates, you just shine two qubit gates with laser together. And at the end, as we will see, I think it already went through. At the end, we read out all the qubit with another laser. You shine a laser on the qubit, you have to tell it's 0 or 1, right, to get your answer. If the qubits actually resonate with your laser, flash back, it means it's in one state. It's actually arbitrarily defined, but we define it as one state. Yeah. If it's not, if it doesn't respond to it, we call it a 0 state. Okay, so how do we trap ion? It's actually interesting because we think if you want to trap something, you kind of dig a hole in the ground and the thing go in there and the trap in there. The electric charged particle is different. We have this glorious Maxwell equation. It says in free space, electric field cannot create a trap. So what do? So we actually use this. So the best you can get is a saddle shape, just like we showed there, right? You see the ball sitting on there, and as long, you can imagine if the saddle doesn't rotate, your ball would fall through one of the falling direction, right? But when you rotate it, it actually always push the ball back to the center. And that's how we act along with Maxwell equation. Even though it says you cannot trap charged particles in free space, we use this rotating electric field to trap it. And because you need this rotating electric field, and you have many, many ions, so you want to control the electric field as good as you can. So we use this, the latest technology as IonQ is using now, as you saw on the title page, is this kind of microfabricated trap. So here I have to show a national lab version because you have this microscope image that shows the specific configuration of how you design each electrode. The key takeaway is each electrode are separate from each other by a small gap, and you can control each of them separately. And why it looks gold? Because you have to make this surface super, super clean, cleaner than anything. No dust at all, no protrude. That's why you coat it with gold. What would happen if you have a dust on it? It sparks. On the scale of the trap, it looks like a micro explosion. It's literally, if you have a spark, that trap is destroyed. That's why it looks like gold. Okay, Now we have the trap. We get the qubit, we get the ion in there. What do we do? What do we use as the qubit? The qubit is actually the internal energy state, internal energy level of an ion. Here I put some elements here in the image. Typically, people draw this kind of wave function of each of the ion, of the electron like this. They form different orbits. That's the language people usually use. And actually, all those electrons are shared the same state. Well, but you can think it as levels. And when it's like that, when the temperature is low, when you control them very well, your transition between each level is very accurate. And it's only react to a specific frequency of light. How can you see that? If you are we are at DEF CON, so you certainly are all very curious. So I bet you have burned the salt, you have burned the metal on the fire, and you know when you burn them, different stuff give out different light. That's because when you burn them, you induce energy into it. You excite them, but they can only jump discrete between this level. So when they decay back, they give you that energy, that frequency of light that correspond to that specific energy gap. So that's what we have. And those energy gap, depending on different materials, can be very different. Some have very stable lifetime. When you pump the energy, when you pump the state to there, it stays there forever. Some just drop like instantly, right? So people have to pick the right species to use as qubit. And luckily, we all have GPS, we have navigation. What is that based on? That is based on atomic clock. The atomic clock community have been studying this for decades. They have found so many ions, so many energy, so many ions that have energy level that is perfect for computation. So typically at IonQ, we publicly announced we use ytterbium and we use barium because they have really good energy level for us to do all the operation, as we will see later. First operation is qubit detection. So all you need to do is to read out whether it's 0 or 1, right? And we mentioned qubits, when it's at the specific level, it only responds to specific frequency of light. So what you do is, for example, here, you define the lower two level, 1 as your 0 and 1 as your 1 state. Here we show f equals 1 is your 1 state. And to read out, you just shine the laser of 369 nanometer laser on it. And then if the laser is in 1, it resonates with the laser. Just like when you burn your metal on the fire, it will give out that specific light. And you collect them with PMT, you amplify your signal, and you know it's in 1. Otherwise, if you don't see that specific color as you burn the thing on the fire, you kind of know it's 0. Okay, and you also have to initialize your qubit. So what we do is this procedure of what we call pumping. Basically, you turn all the lights on, except the lights that couple into your 0 state. And the population, your qubit state, just stochastically shuffle among all of them. But if they get to 0, they trap there because you don't pump it. And that's how we initialize all the qubits into 0. And then comes to the single qubit gate, the first key elements of the gates we talked about. The way we do it, because we use this specific species that has been selected by the atomic clock community as super, super long-lived state. There's a reason they're long-lived, because it's just almost impossible to drive the transition between these two lowest energy level. So we have this magical way called the Raman transition. Basically, you use two lasers to shine them together. Both of the lasers are at 355 nanometer, roughly. And the difference is this energy level. And with this two laser scheme, you can actually drive the transition between these two normally just like day and night, don't ever talk to each other state. And there's another advantage of this, right? Now, we use laser to deliver our message to this super nice qubit state. But at the same time, the frequency we bring down is a difference of it. So we can use optical frequency comp to do it. For frequency comp, only the small difference of that frequency matters. And I will skip some detail and say that allows us to bring down our operation frequency to microwave. That is almost magical. People have been trying to use laser to directly operate qubits for many, many years. It's hard because lasers are kind of nasty. If you, like me, work with them in the lab, they're your best friend and the worst enemy because temperature goes up, right? You just say, I'm hot. But your laser will be like, oh, I gave up. Okay, dude, it's done. Yeah. So because we don't use that anymore, all the information is carried now as microwave. We can use all the microwave technology, super reliable. 50 years of human microwave technology, awesome. That's kind of the success, one key element of success of ion trap technology. Oh, and also, we just happen to have that frequency at 355 nanometer that is using a laser so popular in silicon industry. That is so popular, I'm showing here, you can even buy it on the eBay. How awesome is that? It's like building like a rocket to moon and you can buy your components from eBay. Okay, now that's single qubit gates, right? We mentioned use this Raman transition from eBay laser, you can drive single qubit gates. How do you do 2 qubit gates? The physics is kind of a lot of equation, but I would just say it doesn't really matter. For classical computing, for quantum computing, right? It's a pass of information. As long as there is a way you can pass information from one element to another, there is always a way you can do gates. No matter it's superconducting, no matter it's ion, that's just how information is propagated. So the way we do is almost just like this Newtonian cradle I show on the bottom left. You have the information on each qubit. Each qubit is ion, they are all charged. So they repulse each other. Together, they kind of looks like a spring and they vibrate, and that vibrate is shared among all of them. So when you want to do gate, you shine the laser on one of your qubit. The qubit absorbs the light. Absorbing the light means getting energy, getting that kick. It will take that vibration. The vibration will pass through the ion chain onto another ion. At the right moment when the information passes on the other ion, you shine the laser on it. Yeah? And that qubit will absorb that energy in that vibration into its internal state. That's why you use this collective motion of vibration. You can pass information from one to another. And as I mentioned, quantum, not quantum, whatever, as long as you can pass information with any kind of mechanism, you can do gates. So with quantum, you just need to control the phase perfectly well so it's coherent. So it's just hard by that, but you can do gate with that. I will skip the next one, which is kind of more like a mathematical detail. Basically, to do gates better, a lot of time, we also modulate the intensity of the laser. And another thing, we want to control each of the ions separately, right? So you control each qubit. So the way we do it is we use this acoustic optic modulator. It's a magical like device. It looks like a crystal. When you have lasers through it, you just create some sound vibration onto the crystal. That vibration, together with the crystal, on one hand, will deliver the information will encode the information onto the laser, so it later can be passed to the ion. On the other hand, it can deflect the laser a bit. So we use it to turn it on and off, control the qubit, or in another alternative IonQ's qubit control operation, a qubit control scheme, you can just use it to steer the laser and to directly deliver it onto your qubit. And with all those elements put together, you kind of have a full picture of what is the physics behind all this operation. But that's just the key part in that core ions part. Around it, you need to have electronics, tons of electronics, vacuum, laser, everything controlled by FPGA. I mentioned FPGA because we mentioned the phase, right? FPGA allow us to control the timing of each operation because it's gated with the time. Yeah. So all this electronics, very, very hard. For me, most of the time I mess it up. So I have a huge respect for whoever is expert on this. And that is my friend, Rick, who is going to give the second part. Before I jump into that, I would want to say, if you want to have a hands-on experience on working on ion trap, you can buy those kind of laser board game. Honestly, it's like, yeah, there's no other experience that will give you more similar to how it's like to work on the laser part of ion trap. So kind of a joke, pro tip, so here we go.
All right, thank you, Daiwei. I actually come from a background of building x86 server hardware and firmware, so I don't really know the physics that well. I've had to learn it a lot, and so I mostly deal with the electronics. So we're going to go through the path of software first before we get to the control electronics, because we've talked a lot about the physics of how we're actually going to use the qubits to do computation, but we got to actually get our program in, right? And that's the place that I play. So at the top level, you've got these very high-level frameworks for actually describing your circuits, and a lot of other talks talking about these different frameworks, Penny Lane, Qiskit, et cetera. And all of these frameworks, one of the key pieces of it is that you build these plugins from your individual vendors that actually convert from the abstraction that this high-level framework provides for describing your circuit in sort of an abstract gate model, right, or a particular gate set that's a universal gate set, and takes that and maps it into the API that you're going to submit your job into. In our case, for IonQ, we actually accept it in whatever gate set you want, but so most of this is translating into a JSON request that gets fed into an API service, just like any other API service for any other SaaS application. So that arrives at our API server. And so that initial, so this is kind of the high-level description of what's happening there. You might have a particular circuit, and this would be your quantum circuit diagram that you typically see. The qubits run left to right. Your gate operations are coupling across those. So in this case, it's a Hadamard gate, and then 2 CNOTs, and then a measurement of each of the 3 qubits. So when you write that in something like Qiskit, that's over there on the top right, you're creating a quantum circuit. In this case, it's a GHZ state circuit, does the single Hadamard gate, the 2 CNOT gates, and then a measure all. And when the framework runs and runs it through the IonQ plugin, it's going to generate this JSON request, which is just a very straightforward description of that circuit. And that just gets fed in as, this is what I want to run. But ultimately, the machines, the quantum system, or the quantum computers don't actually operate in any arbitrary gate set. There's this particular set of native gates that we have figured out are mapped very well to the physical manipulations that we were talking about, that Daiwei was talking about earlier. And so it comes into a gate compiler, which does a couple of things. One, it's going to translate between the different gate sets. It's going to re-implement whatever those high-level gate operations are and whatever gate set it's submitted into the native gate set of the system. And of course, that being a relatively straightforward translation, just like if you were to go from C to Python or C to assembly, you might end up with a bunch of redundant operations. And so just like in an optimizing compiler, you're going to go through and do optimization passes to fold together different gate operations and simplify the overall circuit to reduce the number of qubits you need, as well as the number of actual gate operations that you're going to have to perform. So once that optimization pass has happened and you end up with an optimized circuit, that gets tossed into a job queue, because it's we have limited resources on these machines. So this is just an example of taking that same circuit from before, and this is what happens after you apply it to the native gate set of the machine. Now this is done using the SDK. You can actually ask the Qiskit SDK and our plugin to actually do just that direct conversion without applying any of the optimization passes that our actual cloud compiler actually does. But you can see here that we actually turn it into a series of gates like a GPy2, GPy, and MS gates. These are actually the native gates that the machine is capable of actually performing. And some of these where you see, for example, 2 GPy2 gates right next to each other, ultimately that's an optimization where those can be folded together into one operation. So eventually this is going to get picked up by a job scheduler that is running on the quantum computer itself and handed off to the quantum computer. Okay, so this has all been very high-level stuff that would be typical of any software as a service application. So how does the machine actually execute this optimized circuit? Well, we have another piece of software that runs on an x86 machine inside of the quantum computer that takes the optimized circuit in the native gate set, along with a bunch of calibration data, because ultimately the system, even though we've done our best to design it to be very repeatable and fixed in its design. There's just aspects of it that you can't control, and it's going to change over time. And so we run periodic calibrations to figure out the intricacies of individual systems, right? It's characterizing this particular quantum machine at this particular time. We use that to actually do selection of which ions to use for particular operations, because we can choose the best ions if you only need a few of them for your qubits, or we can actually figure out which ones are going to be involved in the most gate operations and use the ones that actually perform the best. Not all ions are created equal in these systems. Once we've actually provided this mapping, so qubit 0 to ion 5, etc., we still have to actually map out the actual gate operations. Now, you saw this diagram earlier, and this little animation. So as we're doing this, we're translating, each gate operation is a laser pulse, right? It's a series of laser pulses, and it actually is coordinated. So not only do you have to deal with creating a modulation pattern on the laser via those AOMs that we talked about earlier, but you also need to make sure that you're actually timing those laser pulses correctly and making them trigger simultaneously. Because remember, phase is very important in this quantum operation. So if those two happen at slightly different times, that accrues additional error in your computation. So this becomes a key aspect. So we actually go through and convert all of those gate operations into individual pulse sequences and schedule them according to a time that they're going to operate within the system. So the quantum control system that receives this quantum program, the quantum program being all of these individual discrete steps of when to turn on certain waveform modulations, etc., gets fed into a series of FPGAs. Now, all of these FPGAs are actually implementing soft processors. They're very custom soft processors with a custom instruction set that is synchronized, and all of the chips are synchronized to a common reference clock. And we carefully measure out signal delays and propagation times throughout the chassis so that the time, the clock edges when they're received at the FPGA and actually inside the FPGA are phase aligned within picoseconds. So even though we actually run at lower frequencies for the actual operation, we know that on a particular clocked edge, we'll have near simultaneous behavior across the entire chassis. So then each one of these FPGAs is doing different operations. We use, for example, AOMs, EOMs, and PMTs, and you have some inputs and some outputs. And unfortunately, this is where my slide development budget went out, so we get some text. So for example, some of the processors that we use in this system, we actually have, and some of these cards are out there and I can talk in detail about the operations of them. But for example, when we need to do those laser pulses, we're actually scheduling an arbitrary waveform generator. And these are actually 16 arbitrary waveform generators per card that are all phase aligned and execute instructions that are time tagged. So that same reference clock that we're talking about back here, we establish a global time reference across the system. We know that this time is incrementing over across the system. We have a characterized signal delay where we can send a start signal and know that that is time 0 across the system. And then we can have everybody maintain a local time step. So they're individually, each processor is individually keeping time, but because the time phase is so closely phase aligned, you don't have much deviation. They all effectively know global time. And each instruction that gets fed into these processors then includes a timestamp of when that instruction should run. So unlike your classical processor, where it's just going to run the next instruction as soon as it possibly can, this will actually stall execution until the precise clock tick where it would happen, so that you can then have multiple processors across the system wait for the same clock tick and then simultaneously execute, and they'll have that operation within picoseconds of each other. So that allows us to use these arbitrary waveform generators to play IQ samples and do modulation, and that's where that generates an RF signal that gets fed into those AOMs to do the actual laser modulation. Similarly, we'll have GPIO outputs that are literally TTL level logic outputs that are used to drive other various devices, turning on and off lasers, turning on and off EOMs. And then on the detection side, we talked about how it emits photons. We actually shine another laser controlled via AOMs again, that when the fluorescence happens, we emit photons, and we capture those photons with photomultiplier tubes. Well, the way we interpret that data back into the control system is that a photomultiplier tube, when it receives a photon on the front of it, it's a vacuum tube, right? And when a photon hits the face of that vacuum tube, it emits an electrical pulse at the back end. So we have implemented a 48-channel universal counter, just like your lab test equipment or electrical test equipment. And it's, again, in the same time system, so we can actually open the trigger gate on the counter at a precise time relative to when we did the fluorescence interval, or the fluorescence pulse. And then we can capture for a very precise amount of time across those channels and measure how many photons came in from each ion individually and present that information back. And that's how you can actually distinguish between 1 and 0 state on the detection side. There's also an entire separately system that is also involved in the same time coherent domain, where we can actually control the the EM field and move ions within the trap. Sometimes we actually, especially during loading operations, when you have that initial ion that you captured, you actually need to slide it down the trap so that you can build out a longer chain. And so we can actually do that with the same level of time control and actually do that mid-circuit. So you could be doing in the middle of an operation and move the ions around and reconfigure things. Is currently an active area of development. So, that's a little bit about the control system, and there's a lot more that can be talked about it. We actually brought one of them to look at and poke at, and feel free to talk to me about all the details. I definitely want to say thank you for having us, and there's a Jupyter Python notebook if you actually want to look at a bunch of the training about how to use the Cloud API and run circuits. And then if you're interested in the SDK and API documentation, there's a link there for as well. Thank you.
Brilliant, thank you, give it up. Absolutely superb. We do have time for a couple of questions, I think, because we've got a good little bit of time between talks. Do you want to come up and give the question here? John, I think you're on your way. That was absolutely brilliant. Daiwei, Vic, absolutely phenomenal. You can see the hardware behind that curtain. Okay, don't go through the curtain, just go round, ideally. But you can actually see what they've been building and see what they've been talking about in this talk. So, question.
Yeah, well, first off, thank you both so much. Both of your talks I thought were really interesting. Specifically, I got to credit, some of those animations were really nice. I wish I had those when I was giving presentations to give people an idea. But I wanted to ask you about kind of in the latter half of the talk when you're really describing the level of optimization you have to do to get these precise timings and this kind of optimal control of these systems. Can you talk a little bit about the methods that you use to facilitate that optimal control?
Yeah, so conceptually the control system, you can think of it as like a VLIW processor. Even though it's actually 30 plus processors operating independently, they're all operating in lockstep on the same timestamp. So you can really think of it as just an incredibly wide processor for independent instructions. And the key to this whole thing is actually regulating the timestamp input to it. So we have that reference clock, which is like a 1 gigahertz reference clock, and we divide it down to 250 megahertz. But the key piece there is that in the distribution of it, we can actually measure the phase delay associated with the different paths. And we can insert delays such that we are able to delay the arrival at each individual chassis so that we may ensure that the clock edge arrives at the exact same time. So the key idea is every single processor is stepping at exactly the same time, or at least within a picosecond or two of each other.
Brilliant. Another question?
So I had a question about the actual loading of the trap. So I guess I'm curious about, you're talking about loading a single ion and then having to move it across the trap, I guess. And I was curious, if you had any problems of losing ions, and what sort of process you do to sort of fix that.
Okay, do you drop ions?
That's a very good question. At the early years of ion trap quantum computing, we have relatively short chain. So there's one thing is if you have a longer chain, they have this nonlinear effect. They accumulate noise and they explode, and your chain is just gone. So when we have a short chain, we kind of have the lifetime of 30 minutes, so we do lose ion. And there's two ways you can go about it. You can either, so our ions live in the vacuum, right? The way you lose it is because there is another nasty, or I just say unwanted, like a bypasser ion, qubits. Sorry, not qubits, atom still in the vacuum chamber and rammed into your chain of ion. That's how you lose it. So there are two ways you can go about it. One is you can make your vacuum pressure lower, even lower. So we're kind of, in terms of the magnitude, at about minus 14, 10 to the minus 14 torr. It's pretty low, but to say it's still not as low as outer space. So there is a possibility to even go lower. So if you go lower, you have less annoying particles ram into your chain. So you can hold your ion longer. And because it's ramming into your chain, that lost it, right? So another way you can do it is you can make those particles go slower. So to make them go slower, you cool your whole chamber down. That's why even people say, in principle, the physics says ion trap quantum computer doesn't have to work in cryo chamber. We still do, we cool it down, but not to like millikelvin. We cool it down to 4 Kelvin, so the energy of each of the running dude is much lower. So even it hits your ions, it doesn't create that significant impact. Then we can use laser to take that energy out. And with that, currently typical lifetime we have nowadays is just infinite. We keep it as long as our laser, as I mentioned, your worst enemy become unhappy and decide to give you wrong frequency. That will cause the loss of ion.
Or until you find a bug in the FPGA and you actually crash the processor that's moving the ion, and then you do lose it too.
Is that called getting CrowdStriked? All right, so thank you very much, Rick and Daiwei. Thank you.